To solve this problem, I mean, my objective is to solve this in closed form in some way. Clearly, I could solve this problem numerically, but what I'd like to do is I'd like to have some closed form expression that tells me something interesting. What I'm going to use is this. So we know that the Gaussian has an additivity property. If I add together two Gaussians, I get a Gaussian, always. The inverse Gaussian, it turns out, has an additivity property as well. If A and B are inverse Gaussian, and the parameters have a certain relationship, then A plus B is also inverse Gaussian. So this isn't a universal additivity property, but it is an additivity property as long as this is satisfied. If that is true, then what we can do is this. Notice that y, this underlying random variable, is the transmitted signal plus the noise. So what I do to calculate capacity is I basically maximize overall possible distributions of x, but this doesn't change. This is just a function of the distribution of n. So basically I'm maximizing overall possible distributions of x of the h of y. Now, one possible distribution is the inverse Gaussian. So if I have inverse Gaussian plus inverse Gaussian, I end up with inverse Gaussian. So I can again express that in terms of the IG of the inverse Gaussian. So the maximum possible h of y is greater than or equal to if I just pick inverse Gaussian.
So the use of the channel in this picture would be that both the sender and receiver have, in addition to having a common clock, they have agreed in advance on a time when they start the whole process.
Yes.
And then X is going to release something, or the sender is going to release something at an unknown time, but according to an agreed upon distribution.
Precisely.
And then sometime later it's detected and, okay.
That's right. I should have said what I'm doing here is I'm maximizing h of y, so the max of h of y is greater than that. So if I just pick a distribution, then the max must, either that maximizes it or the maximum must be greater than that. Okay, the other thing I can do, I can use a property of entropy. Excuse me, I should have mentioned. What I'm doing to get a realistic result is I'm constraining the average of the transmission time. Otherwise, if the average transmission time is unrestricted, if there's no restrictions, then it's easy to show that the capacity is infinite.
For a single use, but
For a single
if
use.
it's the capacity divided by the time that it takes to use
Yes.
the channel, that won't.
That's correct.
Yeah.
Yeah. So there's lots of complicated questions here, but just to get an answer, I'm using this. That's not necessarily something that I recommend. We can also use the following property of any entropy, which is that if the mean is constrained and the variable is non-negative, which is true for y here. If the mean is constrained and the variable is non-negative, then the entropy maximizing distribution is the exponential distribution. So I know that the maximum of h of y has to be less than or equal to the entropy of the corresponding exponential, which is that. So putting it all together, capacity, lower bounded by this, upper bounded by that. Furthermore, this assumes that I'm using the channel as a one-shot. Oh, by the way, Peter, I should mention this is not the paper that we sent to that you reviewed.
Yeah.
It's actually the follow-on paper to that, and this is on archive.
This is very cool. So what happens is if I divide by m and let m go to 0.
Oh, good question.
So some work I did earlier had a result just numerically that suggested that in this kind of channel, making lots of very short and very noisy uses of it was better than we looked for a sort of an optimal signaling time scale by looking at the capacity for short versus long, uses of the channel. Because for longer, you get a more accurate measure of the concentration.
Right.
And the optimal was 0. It kept on going up as you went down.
That's interesting. We have not looked at that, but that would be certainly
I mean, if you've got expressions for these things,
Yeah.
I mean, you can just take the room. And
Yeah, I mean, yeah, we could crunch that out pretty fast, and that's actually not something that I thought of, and that's a really great.
So I'm not reviewing this paper, but if I was, I would tell,
Okay.
I would tell you to do that.
Okay.
Because it should be low hanging, you know.
That's very low hanging fruit. That's something that I hadn't thought of, so that's actually an awesome move. Okay. Okay, so I should note here, this is a one-shot use of the channel. So in other words, I'm taking one molecule and I'm using it to transmit a certain amount of information. This, it turns out, upper bounds the general capacity. So it turns out if you separate everything into individual channels and all the molecules are distinguishable, then this upper bounds the true capacity of the most general case, which is you dump a whole bunch of molecules into the system and you can't distinguish those molecules. So that is a far, far more difficult question for the following reason. So let's start talking about the case where we're not transmitting one molecule at a time, we're transmitting a whole bunch of molecules at a time. So here's my transmission, let's say, and let's say this is a discrete time, and each of these ones, for example, represents a molecule that I dump into the channel, and it propagates to the receiver. So what's going to happen is that these molecules will be delayed. So for instance, if I'm breaking up time discretely like this, I will presumably also want to break up the receiver time into similarly sized bins. So the risk is that this molecule will slip into the next bin before it arrives. So for example, that molecule will arrive in the second bin, not the first bin, which is when it was transmitted. That third molecule might slip 2 bins and arrive there. The fourth molecule might only slip 1 bin and arrive at the same time here, so now I'm counting 2 molecules, and so on. So that molecule, that fourth molecule will slip 2 bins, let's say. The fifth molecule slips only 1 bin, arrives in the same bin. So perhaps I will have transmitted this message in terms of the timings of molecules in this sort of discrete time fashion, but the received sequence will look something like that. But of course, at the receiver, I only get to look at the received sequence. So the question is, how can I go backwards and derive what I transmitted given this? So in fact, it's quite hard, because imagine all of the possible ways in which the molecules could have arrived out of order in order to have been received in that fashion. So, unfortunately, I have bad news. For n particles, simply to write the probability density function of the outputs given the inputs. So the inputs in this case are particle release times, the outputs are particle reception times. If we assume everything is indistinguishable, then I don't get to know in what order, when I observe them at the receiver, I don't get to know what order they were transmitted in. It turns out just to break this down, this probability density function, what I have to do is I have to sum over all possible permutations. So this is the sum over all possible permutations of the received values given the transmitted values. Now that is really bad. So there's this expression under here, under this product. That's the first hitting time distribution. So that could be the inverse Gaussian, like a
But it's discrete.
It's discrete in the example that I presented, but in the general formulation in continuous time, that's just the first hitting time distribution. And then we take the sum over all possible permutations. Now you might be sitting there thinking, okay, I hope maybe there's some more clever way to structure this so that it becomes tractable. Unfortunately, that is also not true. Because this sum over all possible permutations can be expressed in terms of an object which is called the permanent of a matrix. And the permanent of a matrix is known to belong, in computer science lingo, to a complexity class called sharp P complete, which is even worse than NP complete. So, that's the bad news.
Permanent is in permanently insoluble.
Exactly. I think permanent actually comes from positive determinant, because it turns out that if you add the right signs to this expression, it becomes the determinant of the matrix. works, but unfortunately, this can't.
Not because it rises from permutation.
Or maybe from permutations. So here's the formalism that I use to think about this channel.
So let me see if I understand. When you were hoping, naively, you would hope that the capacity for this system would just be like the log of the log of sort of the expected number of particles out there times the other one or something.
You would hope that. I mean, at worst, it's proportional to the other one. Like basically, if
Proportional,
you have,
like the proportionality constant might be 1.
yeah, that's right. So I don't know. Yeah. In any case, here's how I think about this channel. So in discrete time, what I'm going to do is I'm going to feed in an input here. This is going to be a binary input 0, 1, representing a molecule. What's going to happen is that there's a random switch here. This switch, each time one of those intervals comes in, whether there's a molecule here or not, a random selection is made on the switch. And these, if you know anything about linear system notation, basically these represent a discrete delay. That's no delay, that's a unit delay, that's 2 delays, up to n delays. So what's going to happen is that with probability qi, leg I is selected. So that will delay the molecule by a given number of time units, and then everything is added together at the end. So that this is basically how I arrived at this kind of an arrangement. So these delays, they're all added up, and at the output we see this. So each of these transmitted molecules acquired a random delay as they went through, and then at the receiver, all of those delays were added up, as we can see. So I will spare you the details because this talk is getting quite long already. But what we have is this. So I had a graduate student look at this problem, and what they came up with was something remarkable. This capacity, so if you think about it, ideally, this capacity is still intractable. I haven't really done anything to the system, I've simply mathematically formalized it, so therefore the capacity should be the same. But what my student was able to do was simplify it and find a lower bound for the capacity. So we know that the capacity must be greater than or equal to this. So this entire derivation, that one parameter, this px is the probability of sending a molecule in any bin. So I assume that's IID, so this is strictly the IID capacity, which is also a lower bound of the true capacity. This parameter, rho of phi, is a function of those QIs. So I will spare you the details, but the entire derivation basically takes about 4 or 5 pages and is located in that paper, which is quite recent. But I'm actually quite excited about this result because it's a very compact expression related to a single letter in addition to px, which is under our control. So there's some hope here of at least very simply characterizing these channels in terms of a single letter. So why is that important in digital communication? Single letter characterizations of channels are nice. For instance, electromagnetic channels are often characterized by their signal to noise ratio. So that's a single value that basically tells you the quality of the channel.
Can you just say something intuitively about the kind of limiting conditions that give you this result? You had to assume.
Yes. So basically what you do